Session 2, SQL Server 2019, Architecture and Components. So what you will understand by the end of this lecture, in fact, because you guys are also already working on relational databases, so we'll compare it that how Microsoft SQL Server is architecturally different or same or similar to your favorite RDBMS. Major components. SQL Server architecture. Obviously, it is a client server architecture, no surprise, because whenever we talk about these relational databases, all of them are client server model where client make connection, client may be a user, a human, an application, or the request from where the request is coming about managing the database on request on managing the databases and the data. Server is offering the services. So MS SQL Server process starts with the client application sending a request. The server accepts, process and replies to the request with processed data. Basic thing. Major components, there are three major components in SQL Server architecture: protocol layer, relational engine and storage engine. So this is a relational engine where we have CMD parser, optimizer, query executor, where we have query tree generated, query plan sent to query executor. So from where the data is coming to you, if you see, we have protocol layer. So on the top we have protocol layer, and protocol layer is taking the request from SQL Server network interface. So the data is sent in TDS form. What is TDS we'll discuss, and the data goes to this relational engine. In between we have storage engine. Also at the bottom layer we have access methods, transaction manager, then buffer manager, these components, and dirty pages, plan cache, data cache, buffer pool, the flow of the data, physical data storage, the storage part, how it is working. You can see everything with the good arrow, the direction of flow of the data in this architecture. The three components clearly visible in this figure here. That is a protocol layer, the first layer, then a relational layer and storage engine. Three major modules: protocol layer, server network interface, that is SNI, which actually allow the connectivity, what all possible connections, the way you can connect to the SQL Server. That includes shared memory, TCP/IP, named pipe and TDS. We'll understand all of them one by one with real life correlation or real life example scenarios. A relational engine will go through each one of them in detail, and then storage engine, that is file types, access method, buffer manager, plan cache and transaction manager. We'll understand all these components one by one. So protocol layer, SNI. Microsoft SQL Server protocol layer support three types of client server architecture. First is shared memory. Consider this early morning conversation scenario between Tom and mom. Tom and his mom were at the same logical place, and Tom was, "Hey mom, I need a cup of coffee." And mom, "Sure son, preparing, will serve it in next 10 minutes. Tom was able to ask the coffee and mom was able to serve it. They are in the same logical place, same physical place at their home. Microsoft SQL Server here, MS SQL Server provides shared memory protocol. Client and MS SQL Server run on the same machine. So this type of connectivity is possible between same machine. Both can communicate via shared memory protocol. Analogy from the previous figure is, let's map this. We can easily map Tom to the client and mom to SQL Server and home to the machine, and verbal communication is the shared memory protocol. That's how easy to understand the shared memory. From configuration and installation perspective, when we say dot, for communication to local database, In Management Studio, the server name could be dot or localhost or local IP address or machine instance. This will help local connections. The database name dot means the current. So this is a database engine. This can be simple dot here. Significant, it signifies that Microsoft SQL Server is locally installed. So dot refer to the local installation. TCP/IP protocol. Another scenario of the same Tom and mom. In the evening, Tom wants a coffee order from Starbucks, located 10 kilometers away from his home. So today, this time for this purpose, he will make a call. So Tom will call, hello, Starbucks from this. I need a cup of coffee at this address. This is my location. This is my address. So can you send me one cup of coffee for me, or order something? So here Tom and Starbucks are in different physical location. They are communicating via cellular network. Similarly, Microsoft SQL Server provides the capacity or capability to interact via TCP/IP protocol where client and Microsoft SQL Server are remote to each other and installed on separate machines. So compared to this analogy here, we can easily map Tom to the client, Starbucks to the SQL Server, home or marketplace to the remote location, and finally the cellular network, that is telephone, for TCP/IP protocol. In SQL Server Management Studio, for communication via TCP/IP, you provide the server name option has to be machine instance, this form like this server and the machine name and the server. So here SQL Server is the machine name and SQL_MS is the instance name which is running. Remember, SQL Server uses port number 1433 in TCP/IP for connections. Then we have named pipe. At night, Tom wanted to have a light green tea with her neighbor Sierra. Here Tom and his neighbor Sierra are in the same physical location, being each other's neighbor. They are communicating via intra-network. Similarly, Microsoft SQL Server provides capability to interact via named pipe protocol. Here the client and Microsoft SQL Server are in connection via local area network. So here let's map this. We can easily map Tom to the client, Sierra to the SQL Server, neighbor to LAN, and finally intra-network to the named pipe. In the same apartment, in the same building probably, you can simply use the lift or corridor to reach to Sierra, that is local named pipe. For connection via named pipe, this option is by default disabled. We will learn during the installation or post-installation task how to verify what all connections are available and how to enable a specific type of connection or disable a specific type of connection in the SQL Server Configuration Manager. Then we have TDS, that stands for Tabular Data Stream. Sybase also use the same, Adaptive Server Enterprise and SQL Server. This is origin is the same. Sybase is what developed by Sybase. All three protocols use TDS packets. It is encapsulated in network packets. This enables data transfer from the client machine to the server machine. TDS was first developed by Sybase, as I told you, and is now owned by Microsoft. Because that's the question I asked in the morning, because I'm Sybase expert as well. I know the history, how they work and when they departed. So Sybase developed with TDS, it is still used and is now owned by Microsoft. Then we have a relational engine, second layer. The relational engine is also known as query processor. It has the SQL Server components that determines what exactly a query needs to do and how it can be done best. It is responsible for the execution of user queries by requesting data from the storage engine and processing the results that are returned. In the architectural diagram, you could see that three major components of relational engine were there. First was CMD parser. The data once received from protocol layer on the top, which is the top layer, is then passed to a relational engine. The CMD parser is the first component of the relational engine to receive this data from protocol layer. The main job here is to check the query for syntactic and semantic error. Finally, it generates a query tree. So syntactic and semantic and then query tree will be generated. That's the job of CMD parser. So what is this syntactic check? Checking the syntax errors, grammatical errors. So Microsoft SQL has predefined set of keywords in its own grammar, like select is a keyword, insert is a keyword, predefined keywords we have. CMD parser does this check. If the user input does not follow these grammatical syntax or grammatical rules, it returns an error. Then we have semantic check. This is performed by normalizer. In its simplest form, it checks whether column name, table name being queries actually exist in the schema. And if it exists, bind it to the query. This is also known as binding. So semantic check is normalizer and binding the column names with the objects we have. So normalizer performs the replacement of the internally stored view definition and much more. For example, when we say select star from user ID. So select star is no column. Star refer to specific individual columns. So here the CMD parser will parse the statement for semantic check. The parser will throw an error message as normalizer will not define the requested table user ID as it does not exist if this is the case I am talking about. If this is the case, just an example, if the table does not exist. Create query tree. The next phase, this step generates different execution tree in which the query can be run. All the different trees have the same desired output. Then we have optimizer. The work of optimizer is to create an execution plan for the query. You know, the same job, it is a brain. We know that it is a brain, and a lot of study you might have done based on 5 years, 10 years of experience you guys have. The process is no different here. But algorithm is not open source. This is closed source software. So optimization is done for DML like select, insert and delete. Such queries are first marked and then sent to the optimizer. DDL commands like create and alter are not optimized, but they are instead compiled into an internal form. The query cost is calculated based on factors like CPU uses, memory uses, and input-output needs. Its role is to find the cheapest, not the best, cost-effective execution plan. Microsoft SQL Server Optimizer works on inbuilt exhaustive heuristic algorithms. The goal is to minimize the query runtime. Remember, this algorithm is proprietary of Microsoft and it is a secret. It is not disclosed. You cannot understand how it is working. It is working. You just have to agree on, yes, it is working, fan. What is the secret behind it? It will not disclosed. At a high level, searches for optimizer follow these 3 phases. Phase 0, that is trivial plan. Phase 2, transaction and processing plan, that is phase 1. And then we have parallel processing and optimization phase 2. We'll understand these 3 phases. Phase 0, search for trivial plan. What does it mean? It is also known as pre-optimization stage. For some cases, there could be only one practical workable plan. One practical workable plan known as trivial plan. There is no need for creating an optimized plan because searching more would result into finding the same runtime execution plan means alternative plans. There are more plans, there's no point. Like we can know that from here to my milk booth, I know there are 5 different ways, but both will take same time. They are same equally optimized. So let me find out first available smallest plan. That is called uh, trivial plan. That too with extra cost probably if there are other alternatives are available which was not required at all. If no trivial plan found, then the first phase starts. If the plan 0 fails, phase 0 fails, no trivial plan found, then phase 1 starts. It search for transaction processing plans. This include search for simple and complex plans. What all possible plans are there? Complex and simple. Give me both. Simple plan means past data of column and index involved in query will be used for statistical analysis. This usually consists but not restricted to one index per table. Still, if the simple plan is not found, then more complex plan is searched. It involves multiple index per table. It will try to find out that. If this also phase, if both of these above strategies failed, then it will go into the next phase, that is phase 3, parallel processing and optimization. If none of these strategies work, optimizer searches for parallel processing possibilities. This depends on the machine's processing capabilities and configurations. If that is still not possible, then the final optimization phase starts. Now, the final optimization aim is to find all other possible options for executing the query in the best way. And final optimization phase algorithm are Microsoft proprietary. They are not disclosed, as I said. Then after optimization, the query reaches to query executor. Query executor call access method. It provides an execution plan for data fetching logic required for the execution. Once the data is received from storage engine, the results get published to the protocol layer. Finally, the data is sent to the user. So that is query executor will get the data from storage engine, send it to the protocol and send it to the end user, that is a client. So this is a big picture of overall communication. Storage engine, the third layer, last layer. The work of the storage engine is to store data in a storage system disk, like disk or storage area network, and retrieve the data when needed. So we have data files and extents here. That's we have them in Oracle. Similar to that, we have here because that is operating system specific, and all the operating system have, if not same, I can say that I can correlate every storage engine, every architecture of operating system. They refer to the minimum addressable unit that is called block, and then these blocks are used to create extents and the other storage units. So the data file physically stores data in the form of data pages. Dear team delegates, I came from the background where these concepts, the pages were not there. I worked on computer for the first time in 1986. Officially, I started working in 1991 after my graduation in IT. Now, the interesting point I want to share is we used to have a concept called 64K barrier. I still remember that term, I never forget that. The DOS could execute a file of not greater than 64 kilobyte because it used to bring entire data to the memory and the memory was fixed. Because of this constraint, there were limitations, there were restrictions on how big the executable file can be, and this was the problem area. So when we got a new additional driver, the driver was called HIMEM.sys, HIMEM. This driver could add extra memory and which could be understood by operating system. Then came the page concept. paging of memory. So memory also divided into pages, disk also divided into pages, and is something like reading one chapter at a time, one page at a time. So whatever the size of the book is, you don't need to open the entire book, you need one page at a time. Similarly, your eyes have a limitation of reading one sentence or one paragraph or one phrase. So correlate it with that. So one chunk at a time, one page at a time, and once you are done with that, you move that page out, bring up the new page. The concept is same here, data pages. It's much simpler than what it appears to be. With each data page having a size of 8 KB, forming the smallest storage unit in SQL Server. These data pages are logically grouped to form the extent. The maintenance of object is done via these extents. So we first create extents. So one extent create 8 pages. Total size 64 KB. So 64 KB is still the unit here. Interestingly, very interestingly, we still use the same extent size of 64 KB, though now it is divided into pages. The page has a section called page header with a size of 96 bytes carrying the metadata information about the page like the page type, page number, size of used space, size of free space, and pointer to the next page and previous page, etc. Something like you keep index on the first page of your notebook to keep track of what all I have kept in this notebook. So what all file types can be used here? We have a different type of files like primary file. Every database contains one primary file. These stores all important data related to table, view, triggers, etc. Extension of this file is MDF, but it can be any extension. Then secondary file, same. Generally, what we do is in primary file we keep system data also, and in secondary file we keep user data, user specific data, and extension is generally is NDF but can be any extension. Then we keep log file which have LDF as an extension, and we keep logs. This is used for to recover any unwanted instances or transactions. You know the purpose of logs always. So our database consists of log files, file groups, and primary files. Primary file MDF file group is NDF as an additional file group, and log file you can have multiple files in a file group and the log files. This is organization of files in Microsoft SQL Server 2019. Then we have access methods. Access method act as an interface between query executor and buffer manager or transaction logs. Access method itself does not do any execution. The first action is to determine whether the query is select statement, that is the DDL, or a non-select statement, that is the DML, or any other DDL statement which is non-select statement. Depending on the result, the access method takes the following steps. If the query is a DDL select statement, the query is passed to the buffer manager for further processing. If the query is a DDL non-select statement, the query is passed to transaction manager. This normally include update statement. So access methods, DDL, select statement or non-select. Transaction manager will handle non-select statement. Buffer manager will handle the select statement. Much more organized, much more simpler to understand. So buffer manager has its own major role to play here, and in fact that is a very good optimization criteria point to optimize here. As usual, as we do it in Oracle, buffer manager manages core functions of plan cache, data parsing, that is buffer cache and data storage, and dirty pages. So here we have storage buffer manager which takes care of this dirty pages and data cache, buffer pool, and plan cache. Let's understand one by one. Plan cache. Existing query plan. The buffer manager checks if the execution plan is there in the stored plan cache. If yes, then query plan cache and its associated data cache is used. If not, then we'll go for the first time cache plan. Where does existing plan cache come from? If the first query time execution plan is being run and it is complex, it makes sense to store it in the plan cache. This will ensure faster availability when the next time SQL Server gets the same query. So it's nothing else but the query itself, which plan execution is being stored if it is being run for the first time. Then we have data parsing, buffer cache, and data storage. Buffer manager provides access to the data required. Two approaches are possible here depending on whether the data exists in the data cache or not. One is called soft parsing, second is called hard parsing. Soft parsing means data exists, which means data manager looks for the data in buffer cache, and if present, then it is used by query executor. Means we are searching, we call it as a hit in Oracle, that it is a hit. So when we say miss, means it's not there in the cache, so we have to do the hard parsing, means we have to get the data from the disk. If the data is not present in the buffer manager, then the required data is searched in the data storage. That is called hard parsing. So what is soft parsing? Let's understand the same thing. Here, buffer manager is checking the plan exists in the plan cache. If that is the case, then we can get the data from here. This improves the performance as the number of IO operation is reduced when fetching the data from the cache as compared to fetching the data from the data storage or the disk. When we say hard parsing, that means that data is not available in the plan cache. It has to go and fetch the storage. This also stores the data in the data cache for future use, so that it can be used in the next query next time. Then we have something called data dirty pages and a transaction manager. Dirty pages. When you are working on the data, when update is being done, you do those updates in memory. The updated data pages which are not flushed to the disk, which are not sent to the disk, are called dirty pages. A dirty page is stored as a processing logic of transaction manager. And transaction manager is invoked when access method determines that query is non-select statement, as I discussed. So dirty pages have those transaction related pages where updates are happening but they are not final. Then we have log manager and lock manager. The log manager keeps track of all updates done in the system via logs in the transaction log. Logs have log sequence number with a transaction ID and data modification record. This is used for keeping track of transaction committed and transaction rollback. And lock manager, as the name suggests, as you know, the same concept. During transaction, the associated data in data storage is in the lock state. This process is handled by lock manager. This process ensures data consistency and isolation, or ACID, atomicity, consistency, isolation, durability properties. So what is the execution process? Execution process: log manager starts logging and lock manager locks the associated data. Data's copy is maintained in the buffer cache. Copy of the data supposed to be updated is maintained in the log buffer, and all the events update the data in data buffer. Pages which store the data is also known as dirty pages. Then we have checkpoint and write ahead logging. This process run and mark all the pages from dirty pages to disk, but the page remains in the cache. Frequency is approximately 1 run per minute. The page is first pushed to the database of the log file from the buffer log, known as write ahead log. Then we have lazy writer concept. The dirty pages can remain in the memory with lazy writer. When the SQL Server observes a huge load and buffer memory is needed for new transaction, it keeps up dirty pages from the cache. It frees up the dirty pages from the cache. It operates on least recently used algorithm for cleaning the pages from the buffer pool to the disk. That's all for this session. Thank you very much.